Good morning friends. Today I am going to explain what are Maxwell's equations, and at the same time we are going to derive the differential and integral form of Maxwell's equations. This is one of the important topic in Maxwell's equations and electromagnetic waves chapter. Here first of all, what is electromagnetic wave? Electromagnetic wave means a waves in which the electric and magnetic fields are perpendicular to each other. Just here definition is there. The electromagnetic wave is one in which the electric and magnetic fields varies in mutually perpendicular. Now, what are Maxwell's equations? So, Maxwell formulated the basic laws of electricity and magnetism in the form of four fundamental equations, and these equations are known as the Maxwell's equations. The integral and form of these equations is here. First equation is the surface integral of integral of electric field over a closed surface is equal to the ratio between the charge enclosed by that particular surface and the permeability constant of the free space. So first Maxwell's equation represents the, that is, electric field over a closed surface equal to the q by epsilon naught, and the second Maxwell's equation is the magnetic field over a closed surface is always equal to the 0. Next, third law is related to the Faraday's law only, that is line integral E dot dl is equal to minus d phi b by dt, that is the rate of change of magnetic flux, that is electric field is produced due to the rate of change of magnetic flux. And the fourth Maxwell's equation is nothing but it's a Ampere's law only, that is line integral of B dot dl is equal to mu naught times the current I, that is mu naught I. Okay, so these are the four Maxwell's equations. Now we are going to derive the Maxwell's integral and differential forms. Maxwell's equations, integral and differential forms. First, integral and differential forms of Maxwell's equation. First Maxwell's equation. So we know that the Gauss law in electrostatistics is can be given as surface integral E dot ds q by epsilon naught. That is only the first Maxwell's equation only. Okay, so here from the Gauss divergence theorem we know that the surface integral is converted into a volume integral according to the Gauss divergence theorem. So here this surface integral term is replaced by the volume integral. So volume integral is, here we are writing, that is del dot d E into dv is equal to same as it is right hand side, that is q by epsilon naught. Next here we can take out the del dot E outside, 1 dot dv is equal to q by epsilon naught. So I can write 1 dot dv is nothing but a v, integration over the volume v can be given as v. So q by epsilon naught, del dot E is equal to q by, so this can be written as v epsilon naught. We know that q by v is nothing but a charge density, so I can write rho v. Okay, rho v by epsilon naught. So next, del dot E epsilon naught is equal to rho v. So we know that this E epsilon naught or epsilon naught E is replaced by the electric displacement, so that is represented by d. So del dot d is equal to rho v. So let us take, this is equation number 2, and this is nothing but a differential form of Maxwell's first equation. Now integral form. For the integral form, let us take, that is second equation only. So now taking the both the sides volume integral. So volume integral to this equation. Then del dot d over the volume v dv is equal to rho v dv over the volume v. So we know that again we are using the Gauss divergence theorem. This volume integral is changes into surface integral. So already we know this one, according to the Gauss divergence theorem, volume integral can be converted into surface integral and surface integral can be converted into volume integral. So this term is replaced by surface integral, that is del dot ds, and right hand side is rho v dv. So this is known as the integral form of Maxwell's first equation. Now vector form. Vector form can be simply, let us take this equation, del dot d rho v and d dot ds. So this 1 dot dv and 1 dot dv, both the sides get cancelled, then del dot d is equal to rho v. So this is the vector form of Maxwell's first equation. Now Maxwell's second equation. So here we know that according to the Maxwell's second equation, that is the magnetic field over a closed surface is equal to the 0. So we know that this is nothing but it's a gauge line magnetism, and this states that the magnetic flux through a closed surface is 0. Okay, so and this only is known as the Maxwell's second equation. Okay, integral, this is the integral form of Maxwell's second equation. Now for the second equation, differential form. Okay, by Gauss divergence theorem we know that surface integral is can be converted into volume integral. So that is B dot ds can be written as del dot b, or we can say this is inverse div b dot dv. So we can write here this term is can be written as del dot b dv is equal to 0. Okay, next, as the volume is arbitrary, the integral must be 0. We know that over the volume dv is equal to the 0 for the closed surface. So we can write del dot, this total term will be equal to the 0, only we will get div b or del dot b is equal to the 0. This is the differential form of Maxwell's second Maxwell's equation. Okay, now Maxwell's third equation. For the Maxwell's third equation we have to take the Faraday's second law, that is line integral over a curve over a line integral of electric field over a closed curve is equal to the minus d phi b by dt. Okay, the rate of change of magnetic flux. We know that phi b value is nothing but an integral of b dot ds over the surface. Yes, just we are substituting the phi b value into this equation. Then we will get E dot dl is equal to minus d by dt of b dot ds, I can write. So now here again this can be written as, when you take inside the different derivative of this one, then it becomes converted into partial derivative. So d goes to dou. Okay, so we can write dou b by dou t dot ds. This is the integral form of Maxwell's third equation. Now by Stokes theorem we have, so by Stokes, and line integral can be converted into surface integral, and surface integral can be converted into line integral. So this term line integral is we are converting into surface integral. So this term is replaced by del cross E dot ds. So here we are left hand side is del dot d, del cross C, this one is here del cross ds is equal to, this is also del cross minus del cross E ds is equal to minus dou b by dou t dot ds. And next again I can take one ds by s and one ds, both the side ds get cancelled. Then we will get del cross E is equal to minus of dou b by dou t, or del cross E we are calling it, that is curl E is equal to minus dou b by dou t. This is the differential form of Maxwell's third equation. Now Maxwell's fourth equation. Fourth equation, according to the Ampere's law, we can write line integral of magnetic flux over the closed curve is equal to mu naught times current I. So mu naught I. This is only the integral form of Maxwell's fourth equation. Now for the differential form, we are going to take the by Stokes theorem. This line integral is can be converted into surface integral. So surface integral can be written in the form of curl B or del cross B dot ds over the surface. So this term is replaced by del cross B dot ds. So I can write here del cross B dot ds is equal to mu naught I. So if you take outside del dot cross B, then 1 dot ds by over the value of surface integral s is equal to mu naught I. So we know that 1 dot ds is nothing but a area. So area is, I can write in the form of A. So A is equal to mu naught I, and del cross B is equal to mu naught I by, I can write A. Here we know that I by A is nothing but a J, that is the displacement current. So here I by A is replaced by J. So curl B or del cross B is equal to mu naught J. So this is the differential form of Maxwell's fourth equation. The above equation is modified as del cross B is equal to mu naught J plus epsilon naught mu naught dou E by dou T. So this is the modification of this equation by the Maxwell. He added something in the J, current density. So del can be written as del cross B is equal to mu naught J plus epsilon naught dou E by dou T. Thank you. For more videos, subscribe my channel Physics.